All right, this is the last lesson in Unit 7, and we're going to be talking about exponential models with differential equations. We're also going to talk about linear models with differential equations too. All right, so we have exponential growth and decay differential equation, and I'm going to show you what that translates to the exponential equation. So on the exponential equation, it's going to be y equals a sub 0, which is going to be the initial amount. We'll write that down in just a second. And then e raised to the kt, where this is the same k. All right. And a sub 0 is the initial amount. And that's when t is equal to 0. Okay. Great. And then for a linear equation, in a differential model of a linear equation is the derivative is equal to k. It's a constant where that k is the slope of the function. So it's going to be y equals kt plus a sub 0. Same k. Okay. So this first equation is a calculator equation. And we have that the quantity R in grams of a certain radioactive substance decreases according to the exponential decay model dr dt equals negative 0.05 R, where t is measured in seconds. During an experiment, a scientist determines that the rate of decay of a second substance with the quantity S in grams can be modeled by the linear model ds dt equals negative 4, where t is measured in seconds. If at time t equals 0, r sub 0 is 100 and s sub 0 is 125, at what time in seconds will there be equal quantities of both substances? Okay. So R is the one that is exponential. So I'm going to take this information and this information, and I'm going to write an equation for R of t. So R of t is going to be equal to the initial amount, and then E. Now K is going to be this negative 0.05 t. So E raised to that coefficient, and then t. Okay. And then for S, I'm going to take this model and this information to write an equation for S of t. So it's going to be the k, t, and then plus 125. All right, now because this is a calculator question, we're going to use the calculator to find where the graphs intersect. Okay, so just a second. Or I have a ton of stuff open. All right, calculator. Okay, so in Y1, I'm going to put what R is. And then for R2, I'll put what S is. Okay, and then I'm guessing my regular window is not going to quite work. Whoops. Yeah, we're going to need to see where they cross. Okay, so let's just expand it a little bit. Sure. Oh, I typed it in wrong. Yeah, my y is way up in the hundreds. Sorry. Let's try it again. Oh, yay. Okay, there we go. So to find where they intersect, we're going to do the second calc and then pick number 5. And then we can just hit enter 3 times. There it is. So at about 23.548 seconds, they're going to intersect. All right. Then we have a couple of non-calculator questions. So the amount of bacteria in a petri dish increases at a rate proportional to the amount present. At time t equals 0, the amount of bacteria in the petri dish is 10 grams. At time t equals 2, the amount of bacteria in the petri dish is 30 grams. What is the amount in the dish at time t equals 6? Okay, so this is going back to what we learned on the very first day too. So it says that the rate is proportional to the amount present. All right, so going back to writing differential equations, I would say that dB dt is equal to K times the amount of bacteria present, which we'll call B. Okay, so that is the differential equation. And whenever the differential equation looks like that, it translates to an exponential function. All right, we do know that at t equals 0, there's 10 grams. And then we do not know what K is. However, we can use this other information they gave us in the problem to find that. So we are told that at time t equals 2, there's 30 grams of bacteria. So what I would do is take that 30 and put it in for my B of t, and then take the 2 and put it in for t. Whoops, sorry, put it in for t. So that's going to be K that we're finding. All right, and then we haven't done this in a while, but we're going to solve this exponential equation by dividing by 10. All right, and then don't forget that whenever you are solving and we need to bring down an exponent, we're going to take the natural log of each side. All right, so that cancels that. The 2K comes down, and then when we divide by 2, we get what K is, which is the natural log of 3 over 2. And this is a non-calculator question, so we cannot figure out what that is as a decimal, but that's okay. So what I'm going to do is go back to the equation right here, and I'm going to put that in for K. So it was the natural log of 3 over 2, and then we would multiply that by whatever t is. Okay, so to finally answer this question, we want to find the amount of bacteria in the dish at time t equals 6. So we're going to find B of 6. Okay, now I'm hoping you can remember some logarithm rules. But first, it's not a logarithm rule. When we multiply natural log of 3 over 2 by 6, that 2 and 6 reduce to just a regular 3. So I would do 3 natural log of 3. So this 3 came from 6 divided by 2. Oh, I forgot my E. Sorry, guys. Okay, so think back to pre-cal. Whenever you're working with logarithms and there's a number in the front, do you guys remember what you can do with it? You can move it up to an exponent. So that 3 natural log of 3 is the same as natural log of 3 raised to the third, or the natural log of 27. Okay. And then there's another rule I need you guys to remember, which is when you have e raised to the natural log of something, the e natural log almost always cancel each other out. And then you just multiply by that 27. And so your final answer at times 6 is 270 bacteria. Okay. All right, one more. So during optimal conditions, the rate of change of a population of a certain organism is proportional to the population at time t in hours. At time t equals 0 hours, the population is 300. At time t equals 24 hours, the population is 1,000. At what time t is the population 500? Okay, so we're going to call population P. So you guys take a second and write that first differential equation using the information that you're given here. Okay, so if it's proportional, we would say dp dt is equal to kp. All right, and then this type of differential equation translates to an exponential function. All right, so at time t equals 0, the population is 300, and then we do e to the kt. We do not know k, but we need to find it. So we're going to use this other information that at 24 hours, the population was 1,000. So I would put 1,000 in for my P. I put 24 in for my T. Okay. Then we're going to solve by dividing by 300. All right, so that gives us 10 thirds is equal to e to the 24k. Oh, sorry. All right, and then just like last time, we're ready to do the natural log. And they will cancel out. All right, so finally we get that k is that. And because of all of these fractions, I think it might be easier for us to write it as 1/24th natural log of 10 thirds. They mean the exact same thing. All right, So here we go. We are ready to take that value and put it in for our K. Up here where we have this P of T. All right, so the question is, at what time is the population 500? So this is a different problem. This one's actually a little more difficult than the one we just did. So we're finding T. So we would put the 500 in for P. Okay, so again, we do that same step where we're going to divide. Why do I keep forgetting the E? I'm sorry. There should be an E there and an E there. I hope you guys don't do that because I keep doing it. So it's 5/3 equals E to the 1/24th natural log of 10/3 times T. Whew. Okay, so we want to solve for this T. And the only way we can get that down out of an exponent is to use logarithms. All right, so the natural log of E cancels. The exponent comes down. All right. We're going to leave this answer just as a big crazy mess. There's more than one way to give this answer, but it's fine if we just leave it messy. So one thing to keep in mind, like if this was for your response, you can leave it as messy as you want to. We still need to solve it for T, but we don't have to make the answer look pretty. So the answer, I'm going to leave it all these crazy fractions. So it's going to be the natural log of 5/3 over 1/24th natural log of 10/3. All right, that's our time. And I guess it would be in hours. Time is in hours. All right, so your assignment is to do the worksheet that is on the back of this sheet. So you have like a table to fill in, talking about the models, and then writing the corresponding equations. And then you have 5 multiple choice questions.